We're going to go through them, and then we'll just work through a couple problems and then probably call it with that, this section. I just don't see how they're really, truly going to test you that much on this. I'm going to look through like the AP book that I have when we're done going over these problems and just try to see if there's a lot that deals with this stuff, and if not, then we're just going to do a couple problems and keep trucking forward. Alright, so the table that's over here shows the number of seniors who graduated from a high school during the latter half of the last century. Data was not available for all years, especially those long ago. So the number graduated from a particular high school. So first one is to make a scatter plot. Obviously, you really wouldn't need to do it by hand. They did it by hand, but you could just do it by calculator. These. I think these are just the increments they're using. Just, yeah. I'm not really sure. We'll look as we get down to it, see what they're using them for. Alright, so basically we're looking at the number of graduating seniors over here, the number of years after 1950, and so then drawing the sketch. So basically they did like at 39, that was 1989, that's what those numbers are coming from, so it's basically the X values. This is number of years past. Hi. Okay, sounds good. Thank you. No, not right now. I had a first period. I'm not sure where they are right now. Yes, okay. Alright. So basically they just graph all these points, okay? So we're looking at the, like basically kind of analyzing it a little bit, okay? So basically they're increasing until you get to around 1976, and then they have a little bit of a decline, and then they kind of go up again there for this particular school. So then, number 2, these data do not show the size of the graduating class in 1969. To make note the fact that it's skipped there. Create an appropriate model and use it to estimate the size of that class. Explain what years you used and why. So basically, you can do that, remember, on your calculator. It'll get you that equation that's there once you type all the stuff in. Huh? Yeah, so LinReg will get that for you, and then basically wherever X is, you'd type in the number of years, so 1969, so that would, you'd put 19 in there, and then you'd get it out, and it would be about 466 seniors for that particular year. And then obviously you could write down your R and your R squared there as well. If we wanted to project the graduating class sizes through the year 2005, what model would you use? What aspect of these data make you cautious about your projections? So basically, it would probably be the smartest to use things relatively close to that, because obviously if we use stuff from, what is it, like 76 to 89, we would be on a decrease. We wouldn't want to use that. We, at the end, we're currently on an increase of students going up. So we would want to probably use some data close to that. They say the years 89 to 2000 are a pretty good prediction, because that's when it's starting to, come back up on the rise. And then that gives you a pretty decent amount of data to go off of. So basically you would modify that, and you get a modified equation then when you eliminate the rest of that data. So basically you take out everything that is in this upper section, and you would just use these bottom totals here to get a new equation, and then years after, you'd put that in. And so then you would see that there's about 494 seniors there. And then basically they're saying, you need to be cautious because 2005 is basically outside of our data. So that's what it means when it says extrapolated. It's outside of that data. So you'd want to use the data points to estimate, or you'd only want to use the data points to estimate that instead of using all that data because of where it is and stuff in relation. So. Yeah, it's like the O and the L kind of got connected, it looks like. That's not my handwriting, if you can't tell. So, that's normally why I retype the worksheets up, because I just think it's hard to read. So, and then also modify some stuff on it, usually. So, alright. Let's look at a couple example problems, and then I'll give you a couple that are kind of similar to it to try to go off of. Let's start with number 2. Yeah. Alright, so number 2, it has a couple parts to it. So it says, the Center for Disease Control and Prevention tracks cigarette smoking in the United States. That seems to be a really common theme in this textbook. Yeah, smoking and drugs. When the book is updated from the year 2004. Actually, I don't know when this book was done. One of the books that we have is literally from 2004. I think it's a physics book. It's 2005. Yeah, copyright 2010. So when it gets a little more updated. Anyways. How has the percentage of people who smoked changed since the danger became clear during the last half of the 20th century? So if you don't have your book, it's on page, or if you don't have your book out, I would get it out because there's a scatter plot on page 214 that deals with it. So the scatter plot shows percentages of smokers among men 18 to 24 years of age as estimated by surveys from 1965 to 2004. So basically we have a scatter plot that's kind of got a downslope. It's curving though, and it kind of comes back up a little bit. So A wants to know, is there a clear pattern? Describe the trend. Yeah, number 2. So remember, we're looking at basically how has the percentage of people who smoke changed since the danger became clear in the last half of the 20th century. Okay, so is there a clear pattern? Describe the trend. Does it look like there's a pattern based on the scatter plot that you see? Okay, it goes down. Okay, so basically, yes, there is a pattern. Okay, the percentage of smokers. Was at a steady decline. And then until around 1990. So that's what y'all are talking about. It goes back up. There's a slight increase. Is the association strong? And I'm just going to remind you that it doesn't have to be linear. It can be parabolic. Okay, so that was something we kind of got at the end of last section, a little bit in this section. In order for it to be strong, weak, whatever, it doesn't necessarily have to be linear. It can be parabolic. Okay, so based on that, would you say it's strong or weak? Strong? Okay. So yes, it's a strong parabolic association. Okay, and then C, is a linear model appropriate? Yeah, no, because it's already parabolic. Or no, because the shape of the scatter plot. Because it technically is a scatter plot. Okay, it just is a steadily decreasing scatter plot. Alright, number 4. The United Nations Development Program something uses the Human Development Index in an attempt to summarize in one number the progress in health, education, and economics of a country. The number of cell phone subscribers per 1,000 people is positively associated with the economic progress in a country. Can the number of cell phone subscribers be used to predict the HDI? Here is the scatter plot of HDI against cell phone subscribers. So explain why fitting a linear model to these data might be misleading. Yeah, basically data doesn't follow a linear pattern. Okay, the data kind of levels off. Okay, I wouldn't really say this is parabolic necessarily, but from what you guys remember of different types of graphs and different representations, any ideas on what might be a better model for it? I don't really know. Maybe we haven't done a lot of these. Okay, it would be better modeled by a natural log. Okay, so like a log base E, so ln of a value. Okay, that graph kind of looks something more like this in nature. Okay, exponential would be one that goes like this, more so. So exponential would work in some cases with this stuff, but for this one it would be more of a log. Okay, that would fit this data better. Okay, this one, it might be a little bit more confusing. It's kind of just more like what you think is going to happen. If you fit a linear model to the data, what do you think a scatter plot of the residuals versus the predicted HDI will look like? Based on what you see in the graph, kind of. Yeah, like do you think the values are going to be positive, negative, both, start at one thing and kind of end up being something else? What do you think is going to happen? Positive, negative, both. What'd you say, Logan? Okay, so at the beginning, the residuals will be a mix of positive and negative. Okay, but eventually This one's more of like an opinion just based on what you see. It's hard because you're not actually given the data, so you're kind of just going off of what you can see. I would just say whatever you put, explain your reason. Like, so if you said positive, explain like why you think that it is positive. But basically, if you have to kind of remember, like residual versus the predicted is going to be that value that's going above and below. And you're going to have some values that are well below, some that are well above, some that are a good mix. Eventually, you're going to end up, in this case, with all of them being negative. Yeah, negative's an overestimate. Yeah, ultimately, it would be an overestimate. See, they don't really talk about actually finding it if you're just given information. Like, because you'd have to be able to find a linear model. Now, we could do that if, say, like the example on the other page where you were given data, you could figure it out. Like, because you could graph it, you could get your linear regression line, and then you could figure it out. But if you're not given that, it's kind of just, okay, what do you think is going to happen with it, basically? Because there's really no... Honestly, like the book does not talk about what to do to find that. So, that to me says it's an opinion question. Just justify whatever you have to say. And as long as it pretty much makes sense, you're good. Alright, let's look at 8. Alright, movie ratings. Does the cost of making a movie depend on its audience? Huh? Here's a scatter plot of the same data from the problem above. Okay. Okay. Movies with an R rating are colored purple. Really hard to tell the difference in their colors. PG-13 are red and PG are green. Regression lines have been found for each group. The black points are the G-rated, but they were too few to fit a line reliably. There's like 3. I literally can see 3. So in what ways is the relationship between runtimes and budgets similar for the 3 rating groups? So notice basically your X and Y axis. Notice what's on there and tell me what happens. Basically to the runtime and budget. Yeah, budget increases as runtime increases. Yeah, for the most part. I mean, if you're looking at the lines, that's what the lines would show you. Alright, and then B, how do the costs of R-rated movies differ from those of PG-13 and PG-rated movies? Discuss both the slopes and the intercepts. Yeah, so they all have pretty similar slopes. Okay. So, what is true about the R-rated movies compared to the PG-13 and PG? Kinda. Look at their start values. What is different about R-rated versus PG-13 and PG? Their budget. Yeah, so basically what we'd want to say here is that the budget of the R-rated movie is lower because it has a lower starting budget. So if you look at it, it doesn't even cost $1 million for their initial movies that are like really short. But as it goes up at pretty much, you could say, almost the exact same slope as the PG-13. But it starts lower. Its starting budget is lower. So, yeah, so the line, yes. You can look at the dots, but primarily look at the lines because that's an average of all your data. So, basically, the budget of the R-rated movie is much lower because it has a lower starting budget. Okay, so we're going to do one more problem, but I'm going to give you 7, which is kind of similar. Okay, it goes kind of with 8. It just is asking a little bit of a different question. But it's a different relationship. You're looking at dramas versus other movies, whereas in this one we're looking at movie ratings. So, kind of goes together. Huh? Oh, there's a part C. We can just talk about it. I didn't even realize there was a part C. Okay, so the film King Kong with a runtime of 187 minutes is the red point at the lower right side, so it's like way past 100, or well, I say way past. It's past 180 to the right there. If it were omitted from the analysis, how might that change your conclusion about PG-13 movies? Yeah. It probably is an outlier, but overall it's probably not really going to affect it that much in the grand scheme of things because you have that one that's way low and then you have a couple that are a little higher up, so ultimately it's probably not really going to affect anything in regards to the PG-13. You could say, if you were given it, you could probably say, yeah, it's most likely an outlier, but I don't really think you would need to go much farther than that with it in that regard. Let's see. I know. That's the other downside to this book. We'll come back and look at 12 in a minute, and 11 is kind of similar to it. So we'll look at 12 and then I'll give you guys 11 to do. But let's go through and look at 18 first. So 18, a college admissions officer defending the college's use of SAT scores in the admissions process produced the graph below. It shows that the mean GPAs for last year's freshmen grouped by SAT scores. How strong is the evidence that SAT score is a good predictor of GPA? What concerns you about the graph, the statistical methodology, or the conclusion reached? Number 18. So first of all, how strong is the evidence that the SAT score is a good predictor of GPA? So you have SAT scores on the x-axis and the GPA on the y-axis. Yeah. So I would say something like it's, moderately strong. Because it's fairly linear. Let's see. So then, okay. What concerns you about the graph? What do you notice here? What do we normally do when we graph stuff like this? Do we normally connect the dots? No. Okay, it should be a scatter plot. With the dots not connected. Okay, how about the statistical methodology? Basically, like, do you think that this data is, like, accurate? Like, do you think that basically the admissions officer used all the data, or do you think that he used the data that he wanted to use? Yeah, like I did that. I got like a 1050 on my SAT, but my GPA was like a 4.23. So mine would not fit this data line at all. So I would say that it's probably the admissions officer chose data to fit, and I would put that in quotes, his model, okay, to prove his point, okay, meaning the scores and the GPA. Okay, not to say that he 100% did that, but based on what we see, we would probably need to see a true scatter plot to know if he did or didn't. Yeah. I mean, you would really need to see a scatter of them because you are going to have some, and maybe it is that he used it all and then averaged them together. But I'd have a hard time thinking somebody with a 3.5 GPA ended up down with like getting like a 950 and we're marking it down as a 2.25. I mean, it's pretty hard to get a GPA lower than like a 2. So I don't think it would offset it that much. And you are going to have people that have GPAs like that have really low test scores, and vice versa, somebody that does really well on their test, but actually has a really low GPA. I mean, this probably would be more parabolic, honestly, if you were to look at it in terms of that. Yeah, that's what I'm saying. It's really hard to get something below that, and it would be really hard for a 1 to offset like a 3.5, and that based on what they're showing us here. Let me grab my paper from the other day that we used to talk about like the leverage and the unusual points and all that stuff. Make sure they're on this page. Also, so what I didn't realize is that Chapter 10 is the last chapter in this unit, I think. So, Well, okay, so based on, anyways, I now know who my sub is, and since it's not somebody that I really have contact with, I don't really want to leave like a quiz for you guys to do, because if you have a question in the middle of the quiz, I can't really answer it. So, Miss Atkins. Maybe. Hopefully. Anyways, so this is what I'm leaning towards. I'm leaning towards a quiz on 7, 8, and maybe a little bit of 9. We had a quiz on 7, didn't we? Did we have a quiz on 7? I don't know, but we might do a quiz on like 7, 8, and 9 on Wednesday. Okay, so basically we will do a little bit of review on tomorrow. Probably you'll have time to like work on these problems, ask questions if you have questions about them, stuff like that. Friday we'll start reviewing. Monday we'll finish reviewing. Tuesday you don't have school, but I'm not giving you like work to do, but you'll have a quiz on Wednesday, which I don't necessarily want to do that, but I think that's like the best option because then Thursday we can start notes. We'll get to a certain point, and then I'll have like videos of the notes for you to watch. And probably what I'll do is I'll probably also upload the notes on Google Classroom, so if something happens, you can at least get the notes down. And then I don't know. I'll see. I have to look at the Chapter 10 notes and see what I want to do with that for sure. But just kind of a heads up, because I'll be gone for 3 days. So we'll see what that's going to look like for sure. Okay, so looking at, let's look at number 12 here and see. Okay, so we're going to be referring back to this stuff here that we did for these problems, kind of. Huh? Okay, so basically you're going to be given data, and we want to talk about what's going on with it, okay, in regards to the data. So we have 4 questions, and we have 4 different options, so we have to basically do A, B, C, and D for each thing. Yeah. Let me get to the solutions page here to have it handy. Let's see, what question is this? 12? Okay, so actually what they do is they do A, B, and C, or A, B, C, and D, and they do 1, 2, 3, 4 for each one. I think we should just do like part 1, and we'll do A, B, and C of each one, because that way we can do everything for part 1 at the same time. Alright, so looking at this, okay, in what way is the point unusual? Does it have high leverage, large residual, or both? So looking at 1A, what does it look like is happening? You said high leverage. I was going to say, are you looking at A? I'm trying to make sure I'm looking at the right problem. The book is saying this one's high leverage, but I would have thought this one was low leverage. Because based on what we talked about with that stuff, that doesn't really make sense. Yeah. Well, I'm trying to check something here because Okay, well definitely, okay, part 2A is 100, because we definitely have that right. So we said it's influential. That just doesn't make sense because every one that it's similar to is what we said is low leverage. Okay, so maybe we need to go back to this because in the ones we did, we only had 4 points, so I think that's what kind of makes it a little different. They have more of a cluster of points. So point number 2 that we had was that a point is unusual if its x value is far from the mean of the x values. This is called high leverage. So basically in A, our mean is like way over to the right, like of our x values, and that's way to the left. That would mean it's high leverage. Okay, based on that. So I would say try to go more off what we stated rather than the pictures, because I think our pictures are a little different because they only had 4 points. So it's going to be a little different. Okay, and then this one, trying to like get some stuff moved here. Hold on a second. I was trying to see the thing about the residual, making sure. Just don't worry about the residual part. Just look at the leverage or not, and then, yeah. Okay, so part B then. I think that one's going to be low this time. Nope. So the x value is still far from the mean of the x values in this case because you have the point way over to the right and all your data is to the left. So it's still going to be high leverage. Yeah, for 1. Then C, what would you say about it? I would say low. And then how about D? What do you notice about the x value there that in relation to the data, all the data? So what would that tell us? High. So high leverage for that one. All right, so then part 2, do you think that the point is an influential point? Yeah, so influential. Okay, so it's also high leverage and probably a small residual. These are the most troublesome. They aren't consistent with the model. If the point is removed, the slope of the line dramatically changes. Okay, it changes the model. Don't throw it out without thinking. Okay, so basically if we had it, basically if we took it out, it's going to greatly affect what happens with our slope. So our slope is going to change a lot. So we said that A is influential. Okay, already. How about B? Yeah, I would say influential for that one as well. How about C? Not influential. How about D? So this one, because basically if you were to draw a line between that point and the rest of your data, your slope would pretty much stay the same. Because your slope of your line would already be like a negative slope, and if you were to actually draw it, it's probably going to actually go right through the middle of it, so that one we would say is not influential. Okay. Part 3. Okay, if that point is removed, would the correlation become stronger or weaker? It says to explain, but I'm not worried about us doing the explain part. So would it become stronger or weaker? The correlation for A. Yeah. Stronger. B. Yeah, weaker. Okay, because it's kind of way out there. Not really in the direction that we're going. C. Stronger. And D. That one's going to be weaker because it's kind of way out there as an outlier. If we didn't have that, it would probably make it, wait, I think I just said that wrong. It's weaker because if we took it out, it would make our slope change a little bit. It would make our slope a little bit more flat. All right, and then lastly for 4. Okay, if that point were removed, would the slope of the regression line increase or decrease? For A. Yes. Okay, because that outlier is pulling it towards 0. B. Yeah, decrease. It's making it flatter. C. This one would probably really stay about the same. Because it's only one point that's pulling, so it's probably not really going to affect the slope that much to begin with. So taking it out is probably really not going to do anything. And D. Maybe it's probably going to stay about the same. Okay, you could probably make an argument for it decreasing, but I would say probably about the same for that one. Just because if you take it out, I mean, your slope is going to change a little bit, so you could argue the decrease. Okay, you couldn't really argue increase, but you could argue it staying about the same or decreasing, I guess, based on what I can see there. Okay, so the problems, I'm going to go ahead and give them to you now, but we'll work on them tomorrow in class to give you guys time to do them. Let's see. So 1, 3, 7, 11, and 17. So I'm trying to give you guys one similar to what we did today. So there's only a couple minutes left, so you don't really have to do anything, but tomorrow, then you'll work on these problems.